Okay, let's start this session. Okay, good evening, everyone. My name is Arka Roy. I'm working as a Prime Minister Research Fellow in the Department of Electrical Engineering, IIT Patna. And I welcome you all to this third live session on this course named Deep Learning. This course is offered by Professor Pravir Kumar Biswas, who is a professor in the Department of Electronics and Electrical Communication Engineering, IIT Kharagpur. So far, what I have seen is that already I think you've been graded for week 1 quiz and week 2 quiz. I think someone's mic is on. Please turn it off, otherwise, let me see. Yeah. So far, you've been graded for week 1 quiz and week 2 quiz. Rather, week 0 quiz also is there, but that will not contribute in your final certification because that will not be counted for the real quiz. And apart from that, so in this particular session, we will actually try to solve week 1 and week 2 quiz that is there in the course website. I have also seen that they have provided a solution, but as per the guidelines of NPTEL, we also have to give you the solution while doing this particular live session. So I thought of making the solutions for week 1 and week 2 in this particular session, as well as after solving week 1 and week 2 quiz, we will take some problems, basically practice problems to solve that will help you in solving the week 3 quiz that is there in the course website as well. And apart from that, I wrote that Python coding will be doing, but today, as because I have to take questions from week 1, week 2, as well as week 3, so I thought of omitting this today. So probably in the next week, we will be doing the hands-on session on linear machines and SVM classifiers. So whatever problem has been discussed in week 3, for example, you have linear machine. So in case of linear machine, what you have seen in the lecture that you have a weight matrix. So this is W, and this corresponds to basically of dimensionality of D of K cross D, where K is basically your number of classes. Where K cross D, where K is basically the number of class and D is the dimensionality of the feature. Dimensionality of feature. And then you have the feature representation. So this is the W matrix, and this is what is called the feature matrix, which is of dimension D cross 1. That means you have D number of features for any given image, and it will map you to a score value, which will basically tell you that the given particular image or given particular instance belongs to which particular class based on what is basically the highest score value yielding at that particular location of the score matrix, or the rather the score vector. So this was linear machine. And Professor Biswas has already showed you that if you unfold the weight matrix, then you will see the images of the templates, rather the templates of car, the templates of frog, horse, etc. So all those exercise we will do in the next week while doing the Python hands-on session for SVM, as well as for the linear machines or the multi-class problems that has been discussed in the week 3 content. So let us dive into the week 1 quiz. So this is the first question. So in the first question, it has been written that someone is trying to join. Okay, so over here it is written that which of the following is or are the region descriptors. So There are two types of descriptors. In general, we have seen for the so there are two types of descriptors that we have seen so far. That is, one is basically the boundary descriptors, which basically gives you the feature or the description of the boundary of any given shape. And another is basically the region descriptor. So in this particular question, they have given some examples or some instances, and we need to identify which of them are basically the region descriptor. Okay. So Fourier descriptor, it is basically a boundary descriptor. Why? Because Fourier descriptor, if you decompose any signal, let's say you have a square wave, periodic square wave. I just have drawn the one period. So if you try to decompose it using Fourier representations, so you will get n number of uh, obviously truncated Fourier series I'm talking about. If you decompose it with the truncated Fourier series coefficients, then you will get n number of such sinusoids or cosinusoids. Now, if you add up all these sinusoids and cosinusoid, you will get back to the uh, initial representation. So if you just use first two components, Fourier components, you will get somewhat a smoothed version. And if you add all the components, then you will get back this sharp transition based square wave. So this basically gives you the edge information, and that is why this is a boundary descriptor. As well as here we have signature. Signature is what? For example, you have an object, a circular object over here. Then from the centroid, you can so from the centroid, you can actually measure the distance, and you can rotate this particular vector to get the distance for all possible angles. So over here, you will get a descriptor d of theta, which will vary over theta. And for example, if it is a circle, it actually not looking like a circle, but let us consider this a circle. So your descriptor will vary uniformly, as because the radius is uniform with whatever angle you rotate the vector. So this also gives you the hint of the boundary of any particular given object. So this is also a boundary descriptor. And over here, we have the co-occurrence matrix. So co-occurrence matrix is basically used to identify the texture information given any signal. So this is one of such. This is one of such region descriptors. And region descriptors also contain the intensity based features. For example, the histogram. Histogram, what it basically does is it basically gives you a probability of occurrence. So if you take a particular pixel and you note down the pixel value, and then what you do is basically try to get the occurrence of that particular pixel intensity level over the all pixel intensities. So therefore, the intensity histogram and the co-occurrence matrix, these two are the correct options. So option C is the correct one. Okay.
Sir, what is co-occurrence matrix is giving?
Co-occurrence matrix basically gives you the texture information. For example, if you have a image over here, and let's say there is a horse, and over here the color, or let's say you have a image of woven fabric. So somewhere the pattern is like this, and you have another woven fabrics image which has patterns like this. So now you can see that over here in this white space, the pixel intensity or the pixel contrast levels are kind of uniform. However, at this particular location, you can say that the intensity level is changing as because the color values are changing. So over here, you can observe there is an texture discrepancy is there. So over here the texture was somewhat different, over here the texture is somewhat different. So gray level co-occurrence matrix is basically try to capture these texture based descriptions that where the texture basically differs. So as it is basically giving you, okay, within this region the texture is different, so that is why this is called a region based descriptor. And intensity histogram also, for example, you have an image like this which has mostly darker pixels at this particular location and brighter pixel at this particular location. So your histogram will also be biased to, for example, these are basically the black pixel region, and this is basically the white pixel region. So as you go along this particular direction in the x-axis, that means brightness is increased. So over here in this particular region, you will get that all the pixel values will have very low intensity, and over here you will get very high intensity. So again, it basically shows that at which region the intensity value is low and at which region the intensity value is high. So therefore, again, you are getting some information regarding the region of a particular given image. So that is why this is also a region descriptor. Okay. So next question is, which of the following is not a co-occurrence matrix based descriptor? So from week 0 live session and week 1 live session also, we talked in week 0 live session, we basically talked about the gray level co-occurrence matrix and their second generation features such as entropy, uniformity, then maximum probability descriptors and all. However, as well as in week 1 also, while doing the Python coding session, so I used a function to call skimage dot gray comat dot gray co props. So under this gray props, you will get several of the second generation features. So you don't have to write the equations by yourself. So already methods are there. You just call the gray props, and then in the within the arguments you just feed what else you actually require to extract the second generation features, such as you can extract entropy, you can extract maximum descriptors, maximum probability descriptors, uniformity, etc. However, over here you can see this particular option, intensity histogram. Intensity histogram is itself a particular feature, a particular boundary region descriptor. So this is not what is basically derived from gray level co-occurrence matrix. So therefore, intensity histogram is not a derivative of co-occurrence matrix. Okay.
Sir, how
Yes.
many boundary descriptors do we have, sir, total?
Uh, See, there are n number, you can define n number of boundary descriptors, but in this particular lecture, for example, you can use uh, wavelet based decomposition, wavelet decomposition, then any kind of mode decomposition you can use, which will give you the boundary information apart from using this signature and Fourier descriptor. So in general, there are several types of boundary descriptors are there. However, in this particular course, to just show you the glimpse, because this particular lecture series is dedicated for the deep learning. So just to give you the basic idea about machine learning based features, we have talked about few of them, such as Fourier, then boundary, then polygon based representation, etc., etc. So you can find n number of boundary descriptors. But in this course, we have talked about 2 or 3.
And what is entropy here?
Oh, entropy. So over here, for example, you have got a gray level co-occurrence matrix. So let's say for simplicity, I'm talking about a 3 cross 3. I'm considering a 3 cross 3 gray level co-occurrence matrix. So you have the entries such as G11, G12, G13, and likewise it will go up to G33. So entropy is this one. So P into log of P, and then you put a minus sign, and then you sum all the values. So for example, it will be G11, so minus will be there, G11 log of G11, then plus G12 log of G12, and likewise you can extend your summation up to G33 log of G33. So this is a mathematical operation. This basically shows you that how random, whatever randomness is basically consisted within the what you call the GLC matrix. That means how frequent you are getting some texture changes. So if your entropy value is high, that means you have higher randomness, and which basically gives you an interpretation that you have a significant amount of texture change within the image that is given to you. Okay.
Hello, I have one question here.
Yes, yes, yes.
So, whatever region descriptor or co-occurrence matrix is described here, so is that possible to develop a model uh, wherein we can query regarding all these questions and I will get the answers out of that?
Can you repeat your question? What again, please?
So for an example, I have an image, okay, and
Okay.
I need to see based on the texture or any other properties like color or whatever.
You
I
want to
want to query,
classify it. You
I
want to
want to
classify
query
it.
that image. I want to query the image. Just like
Okay.
you can consider vision language model, right? With
Yeah.
vision language model, I can ask any question like how many objects are there or
Yeah, yeah, yeah.
what that
So, so what I have understood is that you want to create a model. In the input of the model, you will give the co-occurrence matrix or something like that, some of the features out of the co-occurrence matrix, and you will try to get to know that if given this is the co-occurrence matrix, for example, you want to classify it to a dog image, whether this feature is coming from a dog image or cat image, like that.
No,
By
yeah, that could be one of the use case, but other use case like whatever questions are described in this assignment, I
uh,
can I can ask same question to the image and I will get the answers like that. I
oh,
can ask, yeah,
like you are asking like something like chat gpt, that
yeah, yeah,
you will have a gpt model, you will feed the image, you will write the question, and it will give you the answer, right?
yeah, yeah.
Something
For
like that.
any property, yeah,
Yeah, yeah. See, the current scope of this party you can get, and I can also show you, because the model has to be trained. It is not like you have some. First, you need to create a model, then you have to train the model, and then you can deploy it in the web, and then you can get that is there in the chat gpt also. Chat gpt was also initially trained, then it was deployed in the web, and then currently what you are doing, if you feed something, you feed some text, it will give some reply. So that I can do, but it is beyond the scope of the course, because this in this particular course uh, it is basically designed in such a way that we'll be focusing on the behind mathematics of the deep
foundation of
learning
the,
problems. Yeah, this is a
okay,
foundational course. What you are
okay.
asking, that is quite advanced level. We can do it, but that is out of the scope of this
Basically, I
particular
have to
course.
create maybe at foundational level. I want to understand like if I want to understand if that image has some kind of texture or what is the intensity of different colors, black and white colors. So I have to create data in that way.
Okay,
For
so
example, there are 255 level of color intensities, right?
yes,
So I have
yes,
to create the image text pair like for zero pixel.
yeah,
This is kind of image for that is for
yeah.
only one property. There are several other properties
There are
like
several other properties. Yes, yes.
texture based. So I have to create that kind
So
of
you
data.
need to, yeah, you need to create that kind of data. I will show you as because you have told me, so in the next coding class or in the next hands-on session, I will show you one use case, but I will not show you that conversational agent kind of thing, which will answer you the question, because that comes with the reinforcement learning. So in this particular course, we'll be totally restricting ourselves in what you call the supervised learning and unsupervised learning, and to some extent will be talking about the generative deep neural networks. But I will show you one use case, that you have a particular image, and then let's say you are extracting different versions of features, for example gray level co-occurrence matrix based features, boundary descriptors, other features such as local binary pattern and etc. Then you are feeding those data. First you are creating the data, then you are feeding those data to a model, and the model is trying to give you the class identification, classification, basic classification. That I
Okay,
will show you.
classification we can
Yeah,
do.
I will show
And
you
then that text
classification.
pair we can, so once we get the classification, then next step in pipeline could be creating text and image pairs.
Yeah, then you can do the text and image pairs. Then you need to train another model. Now in that particular model, as because you are I think trying to create a something like conversational agent, uh, in which you will feed a image as well as some description, and it will give you some reply back that it has the textured information like this and so and so. So you need to train your model, that particular model, that conversational agent, in a reinforcement learning fashion. So there will be associated you will have association of rewards and penalty. You need to optimize the model, and then you can get the you can optimize your model to a certain extent, so that it can give you the better result in terms of the questionability.
Okay, okay, got it. Yeah.
Okay, so in the next class, I will show you one use case, that is classification, because
Sure.
majorly in this particular course we'll be talking about classification. So I'm also
Yeah,
restricting myself
sure, sure.
for the particular coding session also classification only.
Yeah, I just want to understand like these terminologies are rarely, as per my knowledge, these terminologies concepts are very much important,
Yeah,
but those I can rarely see in the literature which is currently written. Like this base risk classifier, I
yeah,
saw very few literatures which talks about these concepts and
yeah.
how that can be applicable in generative AI.
Yeah. Because nowadays the field has shifted to properly like you just feed the raw data, and the model is you are asking the model to learn everything out of it. So people do not extract some handcrafted features and then feed it to the deep learning model. So just they feed the text or they feed the raw image itself, and on the fly itself it tries to learn something. So the middle part, like this GLCM matrix, local binary pattern. So nowadays people don't care about this because deep learning models are meant to be learn, extract or robust features by itself. So that is why
Okay.
you
But if
might
I
not.
want to customize something, definitely I should have
Yeah.
knowledge about that.
Yes. Obviously, it is always preferred that you should have the domain knowledge, because deep learning, after the intervention of deep learning, the domain knowledge or domain expertise uh, is significantly reduced, because for example, you have the deep learning model, you have some kind of data, and you can do the classification. But the data that you are processing, you need to know about like how the data has been generated or something like that. So domain knowledge is
Yeah,
quite
so the
important.
explanation of the results
Yeah,
given by,
explanation of some results is also important. So that is why you can see that nowadays explainable AI has also come into picture. How to generate possible explanation that while doing, let's say I'm talking about classification itself, while doing a particular classification task, where the model actually focuses to get it classified, let's say a cat dog classification, two class classification. Now you give a image of dog, and it processes uh, that yes, the image belongs to dog class. Now where the model looks at, so that is the point of explainability. So that is also another paradigm of the research.
okay, got it. Thank you so much.
Okay, so the next question is, we have this base minimum risk classifier, and we've been given that P of omega 1 is 0.4, and the class conditional probabilities for class omega 1 and class omega 2 are also given, and you have been given the penalty matrices. So this penalty matrix is given, so we need to find the risk of alpha 1 given x. So risk of alpha 1 given x can be written as summation j lambda of ij and then p of omega j given x. And here let me restrict myself to lambda 1j because we have taken action 1, so lambda 1, and j is basically shows the class. So over here, if I expand this one, so I will get lambda 1 1 p of omega 1 given x plus lambda 1 2 p of omega 2 given x. Sorry, this bracket will be over here. P of omega 2 given x. Now you need to, so let me first write the equations. So lambda 1 1 p of omega 1 given x, you can write it as x given omega 1 multiplied with p of omega 1, and lambda 1 2 p of x given omega 2 multiplied with p of omega 2. And for both the cases, you have a denominator term which basically gives you the marginal probability, that is p of x, or the total probability over here. So p of x I can take common. So lambda 1 1 p of x given omega 1 p of omega 2 plus lambda 1 2 p of x given omega 2 p of omega 2. And the p of x, its expression is basically the averaging information given all the class conditional probabilities. So p of omega, sorry, over here it will be omega 1. Omega 1. So p of omega 1 multiplied with p of x given omega 1 plus p of omega 2 p of x given omega 2. Now what we have over here is p of omega 1 we have. So p of omega 2, we can think that the processes are mutually exclusive. So p of omega 2 is 1 minus p of omega 1. So therefore 0.6. So now if you put all these values, so over here you have 1 1 is equals to 0.1 multiplied with x given omega 1. So this is 0.65 multiplied with p of omega 1 you have is 0.4, right? Then what you have is 0.9 over here, then 0.5 and 0.6. Okay. And in the denominator, you will be having 0.65 multiplied with 0.4 and 0.5 multiplied with 0.6. And if you solve all this, you will get 0.5 to 9 point something. So you can just truncate it to 0.53, which is the answer, option C. Okay, so any confusion in this particular question? Because I have seen that many of the participants were raising questions in the discussion forum. So this is how you need to solve. So the main key concept is, while doing the numerical problems, always you have to consider this denominator term, because the denominator term is important because you are doing the base theorem. So base theorem is incomplete without this denominator term. While doing the classification task in the computer itself, while we are coding, so this p of x is same for both the classes. So we often reject it because this is just a scaling factor. So while doing the numerical problems, while solving this kind of MCQ questions, you need to actually consider this denominator term. That is the main concept in this particular question. You have to remember this one. Yes, I think someone's mic is on. Okay, So the next question is, you have given a signature descriptor over here, and which basically varies from 0 to 360 degree, and the amplitude, you can see that the amplitude is uniform over all the rotation. So that means what kind of object could be. Let us consider this is a circle. So, or you can think of a sphere also. So you start from, let's say, from 0 degree itself. Let me just, so you start from this particular direction at 0 degree, and then you can rotate it by theta. And over here, the radius will be same, as because in the circle, the radius is same from all direction, whatever theta direction you choose, the radius will be same. And over here, this r is equals to k. So that is why these descriptors belongs to this particular object. Now, given this situation, the question states that the value of k is 7. So k is 7 centimeter, and you have an unknown shape. So we already have seen that the shape belongs to this particular thing, and they have asked to find the area. So over here, area is equals to pi r square. So pi multiplied with 49, so semi square. So yeah, it is semi. So 3.14 multiplied with 49 centimeter square. So if you just solve it, it will give you 154 semi square. So this is the solution. So first you need to identify that this particular descriptors refers to which particular object, and if you find the object, then you know the mathematical operations for area and any other. For example, if they have talked about you need to find the circumference, then you can do it, because as far as the object can be tractable, then the mathematics of that object is also tractable. Okay. So in this particular question, it states that suppose you have a Fourier descriptors, and the Fourier descriptors of a shape has k number of coefficients. That means Fourier series is an infinite series. So if you do if you do, let's say, Fourier decomposition, so you will get infinite number of sinusoids and cosinusoids. Now they have used the truncated Fourier decomposition. So that is why you are getting k number of coefficients. Ideally, you should get infinite number of coefficients, but as far as the real-time implementation has been considered, then they have comprised the truncated Fourier decomposition, and which gives you k number of coefficients. Now it also states that we have removed the last few coefficients. So you have k number of coefficients, and then you have remove the last few coefficients. So let's say k coefficients refers to this particular whole matrix, and then you have removed the last few of the entries of that particular matrix. So you are left with this much size over here. Now then you use only m number of coefficients. So m is also less than k. That means while reconstructing, you are using, let's say, this much of coefficients. So at this particular stage, what will be the effect in the truncated Fourier descriptors while reconstructing the shape? So as let's say, again, let me give you an example using a periodic square wave. So let's say this is a single period I'm showing, and you are actually doing the Fourier decomposition. Let's say you are decomposing into k number of such uh, descriptors. So the initial Fourier coefficients, you can see they are of low frequency, and down the line the frequency will increase. So if you use just initial, let's say initial m number of such coefficients, now you can see that obviously your output will be, somewhat smooth. as because they have low frequency information, and if you add low frequency components, then you know that the output will be a smoothed output. So over here, let's check. We will get a smooth boundary version of the shape. We will get only fine details. So fine details is not possible because fine details is contained in the lower in the higher order Fourier coefficients. So fine details is not the correct option. Then full shape will be reconstructed. Obviously, full shape will not be reconstructed as because you are using just only m number of coefficients. Option C is also nullified. Then low frequency component of the boundary will be removed, and from the counter of the from counter of the shape. So low frequency boundary will be removed. So that is also not possible because you are using low frequency information only. So how come it will be removed? So this is also the wrong answer. So option A is the correct one. Okay. Yeah. So in this particular question, so you have a image. So let's say you have an image patch rather, and from this particular image patch, let's first uh, create a GLCM matrix. So can anyone tell me that which will what will be the size of the GLCM matrix?
3 cross 3, sir.
Yeah. So it will be 3 cross 3 because the pixel value ranges from 0 to 2. So 0, 1, 2. So these are the quantization levels. So 0, 1, 2 and 0, 1, 2. So GLCM matrix, so GLCM can be defined as a matrix A, which basically gives you a co-occurrence between the pixel pairs I and J, and the matrix is also parameterized by the parameters L and theta, which basically tells you that how many pixel you have to think about in the horizontal direction, and what will be the angle at which you will be focusing on to create a pixel pair. So over here, this L theta has been given as 1 comma 1. So this A ij for 1 comma 1 we have to evaluate. So this will be the GLCM matrix. And what this 1 comma 1 basically means, it basically means 1 pixel to the right and 1 pixel to the below. So that means if I consider this particular pixel value, so my consideration will be I will go 1 pixel right, then I will go 1 pixel down, and then I will try to check the pixel pair. That means this will be my pixel pair. So for all these pixel values, we'll be doing the same. For example, if this is my point of consideration, I will go one right shift and then I will go one down shift, and then this will be my pixel pair. So likewise, we have to check the possible counts for the co-occurrence of the pixel values. So over here, the first pixel pair is 0 comma 0. So how many pairs are there? If I talk about this 1 pixel right and 1 pixel below parameter, so how many pair counts you can see?
1.
Yeah, so this is that pair. So over here, let me write 1. Okay. Now let's try to talk about 1 1. So how many pairs you can see with the same logic?
0.
0.
0, because there is no such pair is available. For example, if I consider this one, this is 1 2, again 1 2, again 1 2. This will not be the pair because it doesn't satisfy the condition. Then 1 0, and for this particular row there will be no option because there is no rows left. Okay, so let's consider for 2 comma 2. So what will be the pixel number of pixel pairs?
3.
3. Yes. So where's the pen? Okay, so 3. So let me just show you the pixel pair. So this is one pixel pair, then this is another one, and this is another one. So these are the 3 pixel pairs, and so the count is 3. Now for the, as far as the first question is concerned, so the first question out of this whole pixel patch was you need to find y minus x, where y is basically this 3 and x is 0. So y minus x will be 3. I think this is fine. I have not written down the question. So the question was you need to find y minus x. So y minus x value is 3. Yeah. Now, in the next question, you need to find the maximum probability descriptors.
Sir, one question.
Yeah,
Now here it is given 1, comma 1. If it is given 2, comma 1, how to proceed, sir?
2, comma 1. Yeah, so let's say I want to fill this whole matrix now. As per the requirement of the initial question, we just need to find y and x, which are the positional values of this point and this point. Now, let us consider I want to fill this whole matrix. So let us start with 0, 1. So I will come to the point that 1, 2 that you have asked already. So let us start with 0, 1. So can anyone tell me that how many pairs are there for 0, 1?
2.
2. So this is one such pair, and 0, 1. So this is another pair. So yes, this is 2. Then 0, 2, how many pairs are there?
1.
Yeah, so this is 1. So let me just try to show you where is that pair. Yeah, so this is the pair 0, 2. So you can write 1. So what is now 1, 0? How many pairs are there for 1, 0?
1.
Okay, so let me just also verify that. Yeah, so this is the pair 1, 0. So over here I can write 1. And let me talk about now 1, 2. So how many pairs are there for 1, 2?
3.
Okay, so 1, 2, this is 1, 2, and 3. So over here you can write 3. Now 2, 0.
1.
1.
Yeah, 1. So this 1. And what about 2, 1?
4.
4.
4. So in this way, you need to find all the pairs, and you have to fill out this whole matrix first to proceed for the second question. So the second question was you need to find the maximum probability descriptor.
No, sir. My question was, in the
Yeah,
question it is given 1, comma 1, right?
yeah, acha,
Yeah.
it is 1,
If it is
1.
mentioned 2, comma 1, then what is the meaning, sir?
So they have to first give you the interpretation. So that is why you can see that 1, 1, basically they try to mean this particular interpretation. So by the same interpretation, 1, 2, let me say replicate this one. So this 1 means 1 right shift, and 2 means you need to go down, and you have to go down by 2 units. So now you need to look like this. So let's say your point of consideration is this. 1 means 1 right shift, and 2 means you need to go down by 2 units. Okay. So at this condition, so you can check whether these two are forming any pair or not. So if that kind of pairing is there, then you can think about the pixel pair co-occurrence. And if that kind of pixel pair is not there, so then you can just use it as a null pair. So
Sir,
in general, yeah,
first
please.
parameter is orientation and second parameter is
It's a rotation.
rotation, sir. Sir,
Second is
rotation means
rotation.
where we should calculate, sir. Rotation means angle theta, right, sir?
Yeah, it is angle theta. In this particular question, they have not given this particular as a angle. So let me show you how to define the angle. So let me tell you, for creating the mathematical problems, you can define anything, but there are some standard rules are there. So the standard rule that I'm showing is defined in MATLAB. So MATLAB co-occurrence. So if you go to the MATLAB website, they have given the specific rule. So you can also create your own rule, but there are some standard rules are available. For example, probably this one or this one. Yeah. So this you can see. I think let me just maximize it. So this you can see. So this one is the shift at which direction you can go. So 0 means that means you can think about this 0 degree, and 0, 1 they have defined, for example, 0 comma d. So this is the parameter. These are the parameters, and they have defined already that if you put 0 d, so then your angle is 0. If you put minus d comma d, then your angle is minus 45. So there are some standard offset values are there by which you can actually calculate the GLCM matrix. But for creating problems, mathematical problems, we can define any sort of logics. So that one such logic has been formed over here. So uh, as because it is L comma theta, you can actually understand that from the theta parameter that it is written in the question, like uh, 1 pixel right, it gives you the direction, but 1 pixel below it is also gives you a direction, but it doesn't comply with any kind of rotation over there. So the theta component has also been written like in such a way that it also gives you a directional information. So for creating problems, they have written it like this, but this is the standard representation. So this gives you different angles. So for example,
What is angle here? 45 degree. 1,
yeah,
1.
so this 0, 1 is 0 degree, minus 1, 1 is 45 degree. So these are standards. Minus 1, 0, it is 90 degree. So they have defined it like this. So in Python also, you will see that while creating the GLCM matrix, either you declare any particular offset, otherwise they will put a default offset. For example, you can see offset is the distance between pixel of interest and its neighbor. So if you do not declare anything, they will keep this as the default one. And if you specifically mention it, then you have to supply this, and you need to see the documentation first. You cannot put anything random, so it will throw an error. So you need to first see that what is the specifications that is given, and then you can employ it into your particular application or your particular code. So these are the standards. Okay. So, so far we have covered the week 1 questions. Now let us move to week 2
Sir, how
question.
to calculate maximum probability in the previous?
Oh, yeah. Sorry, I forget. For calculating the maximum probability descriptors, first the thing that you have to do, even is if similar kind of question comes into the final examination also. So first you need to fill the whole GLCM matrix. So now after you fill the whole GLCM matrix, you can generate the probability. So for example, the probability for 0 comma 0 will be 1 divided by sum of all these values. So what is the sum over here?
16.
16. So over here probability of 0, 0 is 1 by 16. So likewise you have to calculate all the probability values, but you need to actually derive the maximum probability descriptor. So that means if the numerator is maximum, then you will get the maximum probability because the denominator is same for all the cases. So in this particular case, the maximum probability will be for this particular GLCM matrix value. So the probability descriptor will be 4 divided by sum of all the values, which is 16. So it will be 1 upon 4 or 0.25. Got it?
Yes, sir.
Okay, so this is how you need to calculate this particular question. So over here, I think we have covered the week 1 quiz. Now this is week 2 quiz. Week 2. So in week 2, this is the first question. You have two random variables, and the random variables belongs to the Gaussian distribution, which has these particular means and variances. And there are some statements have been written. So let me try to draw these two distributions, which will give you better visual interpretation. So let me call this is x2 and this is as x1. So 0 means your mean is at 0 location. That means over here mu is equals to 0, and over here also mu is equals to 0. Now your sigma is 3. So over here your sigma is 3. That means sigma is basically spread of this particular belly of the distribution or the Gaussian distribution. So more the sigma, that means the distribution is fatter in terms of its belly representation or the hat representation. So over here you can see this sigma is equals to 3, the sigma is equals to 3, and the second one has 2 sigma. So let me try to reduce it. So even though it is not quite proper, but let us consider this is sigma 2. So x2 will be somewhat more thinner than x1, as because the sigma is high, that means the spread will be high, spread from mean will be high, and that is why your distribution will be fatter in terms of the belly representation or hat representation. And over here, as the sigma is low, that means your distribution will be much thinner than x1. So over here, let me first check that which one seems to be correct. So over here, distribution of x1 will be fatter than distribution of x2. That means it is true. Distribution of x2 is fatter than distribution of x1. This is incorrect. Peak of both distributions will be at same height. So can anyone actually give some comment about this particular option? Is it true or false?
False.
Oh, and why?
Which one is flatter? The peak is less.
It's false because area under the curve should be 1.
Yeah, area under the curve should be 1, but what is the peak? What is the value of the peak? Can anyone give me the value of the peak? Okay, so let me try to give you some visualization. So this is a probability P of x. So you have x in this particular direction, and what is the equation for the Gaussian distribution? Anyone?
1 by square root of 2 pi sigma square exponential half x minus mu by sigma square whole square.
Okay, yes. So this is the equation for this particular case. Now we have given that your mu is 0. So at mu is 0, the equation is it will reduce to sigma exponential minus half x square by sigma square, right? Now let us consider that I want to calculate the value at this particular position, that means at x equals to 0, where it is written that mu is also equals to 0. So at x equals to 0 for x1, so the value will be 1 upon root over 2 pi divided by sigma 1, which is 3. So let me let me write in terms of general representation. So sigma 1 exponential 1 half. So over here, as x equals to 0, so it will be 0 by sigma square. So that means exponential of 0 will be how much? 1. So if it is 1, so I can omit this part. That means at 0 location, obviously we will get a peak over here. So for x1 distribution, you have the peak value of 1 upon root over 2 pi sigma 1. For x2 distribution, your peak value will be 1 upon root over 2 pi into sigma 2. And as because sigma 1 and sigma 2 are not equal, that means their peaks are not at same height. So this is the reason that your peak values are different, as because your sigmas are different, and which is why option C is also nullified. So option A is the correct one.
But sir, we can also look at it from area under the curve,
Yes,
right?
yes.
Because sigma is, yeah, okay.
Yeah, go ahead, go ahead.
Yeah, so what I was saying is if the sigma is, if it's more flatter, and if sigma goes smaller, then the peak is obviously going to go up to
Yeah, yeah,
ensure
yeah.
that the will remain same.
Yeah. So your argument is this one,
Yeah,
right?
yeah,
So yes, from this perspective also you can think, but let's say you want to get the peak value itself. So the value also comes from this particular equation, and as because the sigma values are not different, are different, so that is why you can say their peaks are also different. So
understood.
to deal the problem analytically, then you can use this one. Otherwise, this approach is also correct. So you don't have to worry about all these mathematical operations over there.
Understood. Thank you, sir.
Yeah. Okay, so the next question is, probably I have not written the question serially, so it might be jumbled up. So in which scenario the discriminant function will be linear when two-class Bayesian classifier is used to classify the points distributed normally? So you have normal distribution over there, and it is written that in which cases the discriminant function will be linear. So over here the condition is sigma 1 is equal to sigma 2, and this is not identity matrix. So at this particular condition, it will be linear. Over here, the sigma is identity matrix. That means the features are non-correlated. So therefore, over here also you will get a linear discriminant function. Now upon here sigma 1 is not equal to sigma 2, you will get a quadratic discriminant function. So you can say that for 1 and 2 it will be linear, and for rest of the cases, for the third case it will be non-linear.
Sir, one query.
Yeah.
For the first option, you say sigma 1 equal to sigma 2, but sigma is not an identity matrix, means you can represent it as sigma square into an identity matrix. That is some form of sigma square.
So for the first option, it looks like this, let's say. So sigma 1 is equals to sigma 2. That means, and this is not an identity matrix. That means the off diagonal elements are non-zero. So over here, sigma 1, 1, sigma 1, 2, sigma 2, 1, sigma 2, 2 square. So this is the first case, where in both the cases all the values are same, that is why sigma 1 is equals to sigma 2, but this is not an identity matrix. Now for the second case, what will happen is that sigma 1 is equals to sigma 2, but the matrix will look like this: sigma 1 1 square 0 0 sigma 2 2 square. So over there the off diagonal elements will be 0. So this is the representation for these two cases. And it has been shown in the week's lecture that if sigma 1 is equals to sigma 2, for both the cases you will get linear one, linear discriminant function. And if in the more general case, that means for each and every class it may so happen that your covariance matrices are not same, so at that particular condition you will get the quadratic discrimination function. Okay. So in the next question, it states that you have a discriminant function gi of x for a multi-class classification. X is the feature vectors that has to be classified. So what all are the possible discriminant functions? So discriminant function for any sort of classification using linear machine or something else. So the discriminating function should yield a high value or the maximum value. So maximum value. So that means our optimization problem is to maximize the gi of x. So the optimization problem should be to maximize gi of x. So let's say if x belongs to omega 1, so g1 of x should always be greater than g2 of x. So that is what basically this line means. Now uh, previous in week 1 you have seen there are two types of classifiers. That first one is the minimum error classifier. So in case of minimum error classifier, the classification rule is if x belongs to omega 1, p of omega given x, omega 1 given x, p of omega 1 given x should be greater than p of omega 2 given x. That means still the a posteriori probability has to be maximized. So therefore you can directly write gi of x will be p of omega I given x, and it has to be maximized as because gi should be maximized. So that is the rule of discriminant function. Now you have also seen minimum risk classifier. So in case of minimum risk classifier, if x belongs to omega 1, so the risk associated with the class omega 1, so risk alpha 1 given x should be less than alpha 2 given x. That means if you are choosing that your feature is belonging to omega 1, so the risk associated with dealing with that particular class should be as minimum as possible. Now, this problem is now a minimization problem. This is a minimization problem. However, your gi of x has to be maximized. So you cannot directly write that gi of x should be r of alpha given x. That because r of alpha I given x has to be maximized, but your gi of x should be alpha r of risk should be minimized, but your g should be maximized. So to change this minimization problem to a maximization problem, what you do, you take a negative value. So the negative value will ensure that the minus of the risk value should be maximized. So now you can see that in both right hand side and left hand side, the problem is maximization problem. So over here, uh, what are the statements? So risk value alpha are given x, Bayesian minimum risk classifier can used as a discriminant function. So I have already told that directly you cannot write the gi of x as r alpha I of x because risk should be minimized, and in the right hand side risk is minimized, and in the left hand side the g of I should be maximized. So there is a contradiction. In the second case, negative of risk value of the minimum risk classifier used as a discriminant function. So over here that I have already derived that negative of risk value can be maximized. So over here both right hand side and left hand side satisfies the same optimization problem. So over here statement 2 is correct. After that, negative of a posteriori probability. So negative, you don't have to take negative as because a posteriori probability should be maximized. So the problem itself is a maximization problem. So option 4 is the final answer. That is a posteriori probability in the minimum risk, minimum error classifier should be maximum. So option 2 and 4. So option 2 and 4. Option D is the correct option.
Sir, can you explain option 4?
Yeah. Okay. So let me take another page then. Yeah. So in minimum risk classifier, so let's say you have two classes, omega 1 and omega 2, and upon classification you are writing that your feature belongs to omega 1 class. So the condition will be risk corresponding to omega 1 should be less than risk alpha 2 given x. That means if you are choosing your x to be of omega 1, so the risk associated with that will be minimum. Then only you can comment that x belongs to omega 1. So that means this problem is a minimization of risk. Now let us come to the discriminant function theory. So discriminant function for a class I, let's say gi of x. So let's say again you have two classes, omega 1 and omega 2, and you are saying that x belongs to omega 1. So if x belongs to omega 1, the condition will be g1 of x, that means the discrimination function value for class omega 1 should always be greater than g2 of x. So this problem is what? This is a maximization problem. Now you cannot write this you cannot write gi of x is equals to directly is equals to risk alpha I of x, because gi of x should be maximized by the theory of discriminant function. You can see this is a maximization problem. And on the other hand, risk has to be minimized. So that means this is a minimization problem. So you cannot equate these two. So change to make distinction to write these particular terms in the same page, so what you have to do is that this minimization problem you have to convert to a maximization problem. And how you can convert it to a maximization problem? You just negate this particular risk operator, and now you can see if only risk is there, only r is to be maximized. That means if you put a negative, that means it will give you a opposite information. So that means the minimization problem will now be converted to a maximization problem. So in the left hand side it's a maximization optimization, and in the right hand side also it's a maximization based optimization. So that is why you are considering that negative of risk has to be uh, maximized. Now as far as a posteriori probability is concerned, a posteriori probability comes from the Bayesian minimum error classifier. So in case of Bayesian minimum error classifier, so what you evaluate is p of omega 1 given x, or rather p of omega j given x. Now if you say that your x belongs to omega 1, class omega 1, then your decision rule will be p of omega 1 given x should be p of omega 2 given x. And again from the discrimination theory, if gi of x is given and you are saying x belongs to omega 1, then g1 of x should be g2 of x. So in both the places, now you can see both the places the problem is maximization problem. Maximization over here also maximization. So you can directly write gi of x can be p of omega 1 given x, p of omega I given x. So that is why you are choosing this particular statement for that a posteriori probability p of omega 1 x in Bayesian minimum disk classifier can be used as discriminator function. So this gives you option statement 4, and in the last occasion it was giving you the uh, statement 2. So any confusion regarding this?
No, sir. Thank you.
Okay. Okay, so these are very straightforward questions. So you have a two class problem. You have a discriminator function which is given as g of, so it would be y. So g of y, at of y over here, and what is the updation rule. So as far as gradient descent is being considered, so a k plus 1, that means we are basically trying to optimize the weight values. So this weight value is what? This a value. So a k plus 1 is equals to a of k minus eta. Eta is basically the learning rate. So eta and gradient of the loss function. Now, what is loss function in case of a discriminant function theory? So loss function, so I'm not going to the details about the loss function because it is there in the lecture itself. But if you want, I can uh, spend some couple of time over here. Otherwise, I am just referring to this equation itself. So loss function is for all y misclassified with g of y over here. So your loss function can be also written as for all y misclassified, that means minus a transpose of y over here. So now you need to take the gradient, and gradient with respect to what? As because we are changing the value, we are updating the value of a, that means we need to take the gradient with respect to a. So I need to calculate del L by del A. So if I calculate del L by del A, what will come? It will come as minus a. So you have written a transpose over here. You are writing transpose to do the matrix multiplication. That is why you are just writing transpose. So you can omit this transpose term over here also, because now you have just one particular matrix. So you don't have to think about matrix multiplication. So you can just omit this transpose term for all y misclassified. So now just plug in this particular form over here. So it will give you a of k plus eta into sorry, it will be y only. So eta summation of y. So ak plus 1 is equals to ak plus eta into summation of y. So option A is the correct answer. Okay, so in the next question, it has been stated that you have a discrimination function gi of x is a function of a posterior probability. Okay, so they have written the posterior probability like this. Then the following, then which of the following cannot be an f of x? So we know that f should be a monotonically increasing function. So over here, first we need to check which of these are basically monotonically increasing function. Straight away you can give the answer, but let me show you the plots and then I will comment about the final result. So a to the power x with a greater than 1. So it would have something like this. a to the power minus x with a is greater than 1, that means the value is decaying. So the value is decaying, so it is like this. So it is a power x over here, then you have a power of minus x, so you can think the graph is decreasing. So straight away you can see that this function is not an increasing function, it is rather a decreasing function. So this cannot be the function. But let's check the other options as well. So exponential of x, again exponential of x will have the same form as a to the power x, because over here you have the condition that a is greater than 1 and e is itself greater than 1. So you can see that the similar operation, similar graph can be generated. Now for the 2x plus 3 over here, uh, so let's say this is y is equals to 2x plus 3, so the graph will be somewhat like this. So now you can see that every point, if you take the slope starting from the minus section to the plus section, you can see the slope is increasing. If the slope is increasing, that means this function is also monotonically increasing function, it is not a decreasing function. So over here this is an increasing function, this is also an increasing function, this is also an increasing function. However, a to the power minus x is not an increasing function, so therefore this b option cannot be the f of x or the functionality, as because this is not a increasing function.
Sir, what is the difference between posterior and a posterior, sir, probability?
They are same actually. That is, there is no difference. In some of the books, you will see that the terminology has been written as posterior probability. In some of the books, they write a posterior probability. Same with the P of omega. So in some books, you will say that this is called a priori probability, and in some books, it is written as prior probability. So it is just the terminology change. So there is nothing change in terms of mathematical interpretation, they are same only.
Okay.
So this is quite a big problem. So uh, you have points from class 1, you have points from class 2, you have given so the question, first question was you need to find mu1 and mu2, second question was sigma 1 and sigma 2, and sorry, and the last question is you have been told that the probability, the prior probability, so now you can see this is written as prior, but you can see in the lecture, probably in some lectures it has been told as prior a priori probability. So uh, the terminology changes somewhat. So over here you have the prior probabilities to be same. Now at this particular condition, you need to comment about the statements, which of the statements are true. So uh, I want to ask you that have you all calculated this mu1 and mu2 correctly? So if you have calculated them correctly, then I can directly jump to this particular question. Otherwise, I will calculate the mu and sigma for each cases. So if you have calculated it correctly, then I can skip this particular part.
Calculated, sir.
Yes,
Calculated, right? So
yes, sir.
let me just write down the values. So I'm not again calculating the whole thing because it will just take time, and this is pretty straightforward. So mu1 is 10, 8, mu2 is
12, 6.
12, 6, and this is the situation in case of covariance matrix 8.29 minus 0.85 minus 0.85, and over here also minus 0.85 and 8.29. So that means sigma 1 is sigma 2, sigma 1 and sigma 2 both are same, but they are not the identity matrix. This is the second case, and in this particular second case you have also told that you've been told that p omega 1 is equals to p omega 2. So if you see for two class classification, when we do that g1 of x is equals to g2 of x, to find the boundary, then the final equation that comes to our hands is sigma inverse into so over here you have sigma inverse multiplied with w, and then you have x minus x naught is equals to 0, and x naught also there is a very big mathematical description is also given. So half sigma 1 plus sigma 2 blah blah blah, and then you have log of p of omega 1 divided by p of omega 2, and then again some terms are there, so I'm not writing them. You can just straight away see the lecture and get down to all the values. But as far as the problem is concerned, why I have just focused about log of p1 by p2, because p1 and p2 are same, so this will cancel out, and then log of 1, so log of 1 is also 0. So over here x naught is equals to half mu1 plus mu2, and over here you can see that the operation will look like this: minus x naught is equals to 0. So you can see that the line joining mu1 and mu2, so that means if these are the classes, and these are their corresponding means, so this is mu1 and this is mu2, and you join the lines mu1 and mu2 over here. So this omega you can write mu1 minus mu2 over here, and you can see that this x naught is the midpoint of these lines. So x naught is midpoint of this line. So I am drawing this particular decision boundary. So let's say this is decision boundary 1. So is it the correct one? So will I get decision boundary like this? Will it be a orthogonal bisector of the line joining mu1 and mu2? Will it be this one? If yes, then why? If no, then why? So let's say you have these two classes, and these are the means mu1 and mu2, and this is the line joining mu1 and mu2. So this is what mu1 minus mu2 tells, and the decision surface will cut the line into two halves, and this will be the orthogonal bisector. So is it the correct diagram that I have drawn over here? So will the decision, this is the decision surface, so is it correct? And then why no? Why?
Sir,
Any
Because
reason?
means are
yeah,
different.
sigma 1 equal to sigma 2, but not an identity matrix.
Uh, sigma 1 is equals to sigma no in terms of mathematically can you describe or geometrically can you describe that why this is not the this cannot be the decision surface from this particular equation. From this particular equation, can you draw any inference? You have let me tell you, you have if you had the equation like this, mu1 minus mu2 dot with x minus x naught equal to 0. This dot product equal to 0. Let's say you have two vectors a and b. Dot product is 0. That means obviously a and b are perpendicular to each other. Now the decision surface will go through this point, that is x naught over here, and it will cut the line into two halves. So if the equation was this one only, that means mu1 minus mu2 into x naught, this one only, then your decision surface would have been this. But the problem at hand is somewhat different. Your equation is sigma inverse mu1 minus mu2 x minus x naught is equals to 0, where x naught is equals to half of mu1 plus mu2. Now let me show you why this is not the case. You have two classes. Again, this is mu1 and this is mu2, and this is the line joining mu1 and mu2. This is the line joining mu1 and mu2, and this equation of this line mu1 joining mu2 is mu1 minus mu2. Now let us consider in terms of a vector space. In a vector space, in the last class, in week 0 class, I showed that if you have a vector a, let's say x comma y, and if you have a matrix, let's say a b c d, and you take matrix multiplication a, let me rename it w. So if you take a matrix multiplication w dot a, you can take any matrix after this particular live session. I would request you to take any vector xy and any w, and you do a matrix multiplication. You and then whatever result you will get, let's say z, you plot it again in the vector space. So your vector will be somewhat rotated. Let's say the vector will be rotated at this particular direction. So over here, initially your vector was like this, but while multiplying with some another matrix, you can see your matrix has been what you call your matrix has been rotated. So rotation effect you can see. Over here, the same thing is happening. This line was mu1 minus mu2, but at this particular condition you are multiplying with some matrix. Sigma inverse is also a matrix. So whenever you multiply this vector with a matrix, your vector will be somewhat rotated. Now this is the rotated vector. This is sigma inverse mu1 minus mu2, and now initially this was the midpoint, that is half mu1 plus mu2. Now as because your line has been rotated, now let us consider this is the position of this is the midpoint, as because your line has been rotated, so your midpoint is at this position. So your initial decision surface would be this one. So this is orthogonal to this, but at this particular position, while you are multiplying with sigma inverse, so the decision surface will be perpendicular to this red dot. Got it? So that is why statement 1 says decision boundary passes through the midpoint. Till this point it is okay, of the line segment joining the means of two classes. Okay. Decision boundary will be orthogonal bisector of the line joining means of these two classes. That means they are referring to this particular, this dotted condition. Means of two classes, line joining means of two classes, and they are saying it will be orthogonal bisector. But what you have done when at the moment you multiply with the sigma inverse, your line has been rotated. So that means this decision surface will be orthogonal to this new line, not this previous line, which was mu1 minus mu2. So that is why option 2 is incorrect, option 1 is correct. So this thing you can visualize by yourself also. You just take a vector, you take any matrix, multiply these two, and you will see that the vector will be rotated at some particular angle. It depends on what ABCD value you choose, it will be rotated. So that means this is the thing that is after rotation, this is after rotation, and decision surface will be perpendicular to this particular rotated line, not the original mu1 minus mu2. So that is why option 1 is only true. Okay. So over here, the question is, you have again the same points, class 1, class 2, and you've been told to do a KNN based classification with a K value of equal to 3, and the distance metric that have been given is a Manhattan distance. So this is basically the summation of the absolute distance from each of the coordinates. So you can do it mathematically, but the easy way to do it is to solve these problems graphically. It will save time in the final exam also. So you can roughly draw any grids of, let's say your highest value is 15 over here. So you can draw, you can uh, roughly sketch 15 by 15 grid, and then you can start plotting the points on top of the grid. So let me show you 11 by 11. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 over here. And this 15, 14, 13, 12, 11. So this is 11 by 11 over here. Then you have 13, comma 11. So 12, 13, 13, comma 11. Then 8 comma 10. So over here it is 11, 10, 9, 8, and it is going to 10th position over here. Then you have 9 by 9. So this is 9. So this is 9. And then 7 by 7. So it is 7. 1, 2, 3, 4, 5, 6, 7. Over here it is 7. Then you have 7, comma 5. So this is the next point, and you have 15 comma 3. So over here this is 15. So 1, 2, 3. Okay, so I have plotted each and every point that is there in uh, class 1. So class 1 I have given the cross mark. Now you have class 2, 7 comma 11. So this was 7, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this is first point. Then 15 comma 9. So this is the 15th line. So 3, 4, 5, 6, 7, 8, 9. So over here the next sample. Then 15 comma 7. So this is 9, 8, 7. Second sample. 13 comma 5. So 15, 14, 13. 1, 2, 3, 4, 5 over here. Next point. Uh, 15 comma 13 comma 5 we have drawn. 14 comma 4. So 14, 1, 2, 3, 4 over here. And the next point is 9 comma 3. So this is 11, 10, 9, 1, 2, 3 over here into 3. And 11 comma 3. So this is 11 1 2 3. Yeah, so this is the situation, current situation of two classes. So this class I have denoted by this green dot. Now let me show you one sample case. So in this particular sample case, your sample, unknown sample 6 comma 11. So over here it was 7. So 6 comma 11. So this is the situation. Now you can you classify with using nearest neighbor of 3. So let me show you some possible neighbors. So you can think this as one pair of neighbor with 3 neighborhood. Then you can think of this is the second neighborhood, and you can think of other case. This is the 3 neighborhoods you can get, and from these 3 neighborhoods you can see that number of uh, neighbors are basically the x belongs to class omega class x or class 1. So you can say that it can be classified, a can be classified to class 1. Similarly, your next point, let me uh, draw it with another color, 14 comma 3. So over here this is 14, this is 14 1 2 3. So this is the 14 comma 3. Now you can declare one neighborhood like this. Okay, your second neighbor could be uh, something like this. Your third neighbor could be something like this. So with all these neighbor conditions, you can see you can classify this blue point to class uh, class omega 2 or the class dot. So over here A is 1 and B is 2. So by graphically also, I would suggest you to do these kind of problems graphically, because it will help you to visualize the problem. And as far as your coding session is being concerned, so if you try to implement these problems in real life situations, so you need to have a better hand on this visualization things. So it will help you more to visualize the problem rather than doing it analytically. Analytically you can do, but it will take time, and it will just be a mathematical problem. But alongside this mathematical or analytical aspect, I think you should do the visualization part also. Okay, so
Sir,
yeah,
previous question, one query.
yeah,
So the blue marked line, sir.
yeah.
So we have marked 3 neighbors. So can we take one neighbor as on top? There is one dot, right? So if
This one,
yes, yes, sir.
yeah,
Yeah.
yeah, we
So
can do
then
that.
yes, sir. So graphically we find that is also possible, but then when we take it analytically, there might be some differences, no, the distance and everything.
Yeah, yeah,
So
yeah, yeah. So that is what I am saying, that if you go by analytically, then you will get a pinpoint solution. That means
okay.
there obviously you have to calculate this Manhattan distance, and then you will decide the neighbors. So I am showing the all possible scenarios. I am not calculating the Manhattan distance. So obviously, for example, this last one, which I am now drawing with solid line, this cannot be the situation. So it might happen that only these two cases I can consider. So over here you can consider in number of situations, but if you do analytically, then you will get to a more pinpoint solution. So you can consider several group of features, and out of which you can see that okay, in most of the cases it is classified to dot or green dot class. So that means it belongs to the class 2.
So my query is at the time of programming, don't we consider this Manhattan distance, or is it just graphically?
While coding, so you can see there is a distance called Manhattan distance while coding, or let's say if you are writing this KNN classifier from scratch. So you can use two methods. There is a inbuilt library scikit-learn. So you can just call sklearn KNN and you can pass some arguments, that is x training, then corresponding labels, because you need to have class, whether you need to know that whether the data points belong to class omega 1 or class omega 2. So you will have features as well as the labels y training, and you can even declare a particular distance metric. It could be Manhattan, it could be Moholy-Nagy distance. Moholy-Nagy distance. So Moholy-Nagy distance you have seen in what you call week 2 class, and you can define Euclidean distance. So there are several distance metrics are also there, because while solving this particular problem back in 1980 or something, so they had used different variety of distance measures, because if you change the distance measures, your result will also be affected with that. So they have used different kinds of distance metrics. So you can also improvise with different kind of distance metrics over here. So while coding, if you are writing the code from scratch, then you can define your own sort of distance. Otherwise, if you are using some standard libraries, so they have given the flexibility that you can just call any of the distance. So you need to write in terms of an string that let's say Manhattan. So you just pass this string, so the code will understand, okay, I need to use this particular distance matrix, and based on this distance metric, I will classify the unknown sample. So that is how the code works.
Sir, sir, if k is other than 3, let's say 2, 1, then
Okay, so KNN can be classified into two or three subclasses. One is coarse KNN. That means you just want to classify a particular sample just by looking at its nearest neighbor. That means the situation will be like this. If you have a sample over here, you will just see this particular sample, and then you will be classifying it as um, as it belongs to class omega 1. But that is not a very good choice, because for example, um, you have two classes, let's say husky. Husky is a dog, it's a, breed of dog, and let's say another image, or let's say you choose Enold and black buck. So they look kinda alike. Now let's say for a training samples, your class is distributed like this, and for omega 1 class is distributed like this, and the class omega 2 is distributed like this. Okay, now your unknown data point, let's say your unknown data point is this one. Your unknown data points belongs to class omega 2, but you just want to see in terms of nearest neighbor, single nearest neighbor. So it is basically surrounded by this all red points. So your classification result will be this thing belongs to class omega 1, which is a wrong decision, as because you are not you are just looking at a single neighbor. So instead of that, it is always preferred that you choose a certain number of neighbors which is greater than 1. So if you choose k to be 1, that is called coarse KNN, and then as you keep on increasing the k value, then you go to a finer KNN. So over here, you can see that k to be 1, is doesn't give you a better result. So in the lecture also, I think Professor Biswas has shown you one such case. So over there, if you chose to be, if you chose k value is equals to 1, that does not give you a better result. So it is always preferred that you choose k value is greater than 1. So you can choose any number of k value, that is a hyperparameter. So as far as code is being concerned, you can set k value to be anything, and then you can just plug and play with different values of k, and you can see the classification performance. And from there you can take the you can consider that particular k value for which you are getting the maximum classification accuracy. So that is how you can choose k. Okay, so by this we have covered the week 2 lecture over here. So
Sir, is it
yeah,
required to select the k value as a odd value only, or is there any reason?
uh, by rule of thumb, people basically choose this k value to be 3, 5 like this, but you can use what you call any value, even value also. Just the thing is that you need to check what you call that for which k value. Let's say you can choose that one particular technique is there, it is called grid search CV. So you choose a wide range of k value, let's say 2, 3, 5 up to let's say 50, let's say 50. Then you train knn for each k values, and you record the classification accuracies. Let's say for k equal to 2 you get 90%, for k equal to 3 you get 95%, likewise. So you have a chart of or a table of classification accuracy corresponding to each k value, and then you find for which k value you are getting the highest one. Then you can consider that particular k. Now that particular k could be even, could be odd, anything. It is just to experiment with different k values. You can use any value, it not necessarily to be 3, 5, something like that. You can choose anything. So when you go to the deep learning lectures, you will see in many cases the filter number people basically choose 32, 64 in the order of 2. So that is also a kind of rule of thumb. So you can choose any values. Let's say you can choose filter value, number of filters equal to 50 also. So that there is nothing wrong in there. You can choose any value. Okay.
If we choose even number, then chances of getting both the classes same will be more, right, sir?
Again, that I cannot say because it has to be experimented. It is in the next class I will show that if you change the number of k values, your classification accuracy in some cases it can be degraded, it can be better also. So finitely you cannot say anything. You need to, because let's say any deep learning machine learning problems, let's say MNIST dataset, it has 60,000 images. So for 60,000 images, you cannot just directly say that if I choose the value to be this, then only I will get the maximum accuracy. So you need to experiment with different range of values of k, and then you need to get the results. You need to look up the results, and for which value of k you are getting the highest accuracy, that you have to take. That you have to take as the optimal value of k. So in terms of machine learning, deep learning problem, it is very hard to finitely say that k value should be this, then only you will get the highest accuracy. Because as far as the problem changes, your hyperparameter values will also be changed, will also change. So that is why this term is called hyperparameter. So it comes hyperparameter optimization. That means it could be any value. Then you try to optimize the value of k by using grid search CV and all. Because I don't want to include these things right now, because in the subsequent deep learning lectures you will see by yourself that in case of CNN or in case of artificial neural network, you will be dealing with the hyperparameters and how to tune the hyperparameters. So you have to experiment with these values. You can choose any value and you need to check that, okay, for this particular value I'm getting this. For let's say k equal to 2 I'm getting 90%, k equal to 4 I'm getting 98%. So at that particular condition I will choose k equal to 4. So this is the way you have to do this.
Okay, sir.
Okay. So by this we have covered week 1, week 2 quiz. Now let's move to week 3. Okay, last question. So you have four class problem, and how many discrimination functions will be there? In our lecture we have seen if I have two classes, I will have two discriminator functions g1 and g2, and I need to solve these two equations, linear equations, and then I will get the final classification, final boundary. So that means if I have two class problems, then I will be having two such what you call two such discriminant functions. Similarly, for n class problem, I will have n number of discriminant functions. So over here, n is equals to 4. That means your discriminant function will also be 4. Straightforward. Okay. So from here, we'll start with the what you call week 3 questions. So let me start with some interesting problems first. So can any one of you actually summarize in what is there in week 3 content? What are the topics has been covered in week 3?
Mostly concentrated in support vector machine.
Yeah, so in the first lecture, in the first two lectures, it was support vector machine, and it was professor has given the mathematical concept behind how to construct a support vector machine, how to do the optimization, how to form a Lagrangian, and how to solve that particular Lagrangian to get the optimal solution of an SVM. And then we have talked about the linear machine, which basically has k number of, if you have k number of classes and d dimensionality feature vector, then you will have k such discriminant functions. You solve it in terms of a matrix and you will get a score. And from there he extended the problem to multi-class SVM and covered the new set of loss function that is called a hinge loss. And hinge loss has a specific structure that it is kind of a ReLU structure, but it is a shifted ReLU. Okay, so based on whatever the week 3 content has been covered, so I have taken some of the questions which might help you in solving the final quiz question. So let us start with this particular question. You have given the XY coordinates, that means which are the features. You have two features and you have the class levels. That means either it will be class 1 or it will be class -1. And you need to construct a SVM, you need to construct an SVM boundary. So let me start plotting them. So at max you have 2, so 0, 1, 2, and over here also -1, -2, -1, -2, 1, 2. Okay, let me start plotting them. So it is 1, 0. So over here, then 2, 1. So 2, 1 over here. Then what you have is +1, 2, 0. Okay. Now let me draw for the class of -1. So this is the -1, 0, and then the next point is -1, 1. over here. Okay, so what is the main aim of SVM? Can anyone comment about it? What is the main aim of an SVM classifier in terms of finding the decision boundary?
So there can be n number of possible boundaries to classify data. So take one optimal boundary that classifies the two of the classes is the aim of this SVM.
And in terms of what you are talking, in terms of what you are referring to the optimal solution, there is something, some metric is there. So what is the metric by which you are choosing that the hyperplane should be optimal one? What is the name of the metric?
Margin.
Yeah. So SVM's main target is to maximize the margin. And let me just before going to the this particular problem, before solving this particular problem, let me take another case. So these are the two classes. Okay, so let me consider this is the optimal SVM solution. This is SVM solution. Now, which of the points are called as support vectors? So you have points, 4 points from class 1, you have 5 points from class 2. So which of these points are called as support vectors?
So maybe the point of those of the vector which is larger from the decision boundary are the support vectors.
No, it is just the opposite. So let me give you the explanation. So let's say this is the SVM solution, and you need to maximize the margin. And maximize the margin in terms of what? Maximize the margin in terms of you have to do the correct classification. So let's say from this particular point, if I calculate the distance from this line to this particular point, orthogonal distance, so obviously it has higher margin. Similarly, if I calculate perpendicular distance or orthogonal distance from this point to this point, I can see I have enough margin. Margin values are higher. But for those points, for which the uh, margin value is minimum, that means if I take a line over here and if I just go beyond that, I will start misclassification. So those points are called the support vector. So over here also this has the lowest margin. So that means if I uh, move this particular line till this particular position, and if I just go beyond this, I will start misclassification. So that means this is the range at which I will not do any kind of misclassification. Over here, this is called the margin, and the nearest point to this particular decision surface, which has the lowest orthogonal distance. So those points are called the support vectors. So over here, these are the support vectors, because after these points you have enough margin, because for example for this particular case you have enough margin. For this particular case, again graphically you can see you have higher margin. Over here also you will get higher margin, but for this point and this point, for these two classes, you are getting somewhat lower margin. So these are the boundary points. If you go beyond that, you will start misclassification. So these nearest points are called the support vectors. So over here, yes.
So one query,
Yeah.
how do we fix the margin?
To fix the margin, I think you have seen that let's say you take a vector over here, a point over here, and this is okay. Let me draw another diagram. So this comes with an optimization problem. If you have seen the lecture, so let's say you have a optimal solution. Let's say you have an optimal solution like this, but the lines doesn't seem to be optimal. So from class omega 2, you take a point, let's say x minus. From class omega 1, you take another point x plus. Now you join these two by a vector like this. And for each and every line, you have seen in the discrimination function that you can write a line equation wx plus b equals to 0, and you can absorb this b into this w term itself. So you can directly write in terms of matrix representation w into x is equals to 0. So that means this w into x equal to 0 again will give you w dot product x dot product is equals to 0. That means w is orthogonal to x. So over here you have an orthogonal vector uh, onto this particular line. So let me consider this as a orthogonal vector which is w, and if I take the unit vector along this particular direction, what it will be? It will be of w divided by w norm, right? Now margin is what? Margin is distance from this point to this point. Now if you see graphically, you have a arrow joining x minus and x plus, which is this. It's a bit difficult over here. So you have 2 points x minus and x plus, and you have got a vector over here, and you had a unit vector. Now this unit vector, as per the vector theory, you can shift a vector parallelly to any direction. So over here, if I shift this particular vector parallelly to this particular location, it will not be a problem. And then I can also shift the vector across the diagonal also. So the vector is oriented like this. That is omega divided by omega norm. Okay. Now you need to calculate margin, that is distance, orthogonal distance between these two lines. This is called margin. Now how to get this margin? You can see from the vector algebra that if you take projection of this particular vector, let's say this is v1 and this is v2. If you take projection of v1 on top of v2, then you will get the distance from here to here. That means if you take projection, that means if you take dot product between v1 and v2, then you will get the margin value. So margin is equals to dot product between w norm multiplied with this particular vector. So this particular vector is what? You can write x plus minus x minus. Okay. So this is basically the margin. Now the equation that you have seen probably in the lecture itself, you can write w into x plus b, x plus b is equals to into multiplied with yi should be 1 for class omega 1, and wi into omega x minus plus b is equals to minus 1. So if you negate these two solutions, then you can actually write it that. Otherwise, let me consider this y could be nullified. So w multiplied, if you take one a minus b, so it will be x plus minus x minus will be equal to 2. So over here you can see that w dot product x plus into x minus is equals to 2. So you can write 2 by norm of w. So now you need to maximize margin. So the problem is now maximize margin. That means maximize 2 by norm w such that it follows the particular condition. That means yi w into xi plus b should be greater than 1. So you need to maximize this margin. So your how you can maximize, as you asked, you have to maximize this with subject to constraint that you have to follow this particular rule also. So this is called a constraint optimization problem. So for that you need to form a Lagrangian, and then you have to take derivative of the Lagrangian with respect to w, and then you can solve the equation. You have to take Lagrangian factor will also be coming alpha I, and then you have to do all the derivation. So the derivation is there week in week 3, probably lecture number 2. So you can follow that particular lecture. Professor has already showed that how you can maximize this particular margin value. So the derivation is there. You can refer to that particular derivation. Okay. So as far as this particular question is being concerned, you can see that if this is to be the midpoint, because the first position is 1 and minus 1, so margin will be maximized because these two will be the support vectors. For if I choose x is equals to 0, then I can see that I have a margin of value 2 over here, and at that particular condition my support vectors are minus 1 comma 0 and 1 comma 0. So at that particular condition I can see that my margin is the maximum one, that is 2, and I am correctly classifying all the samples with this particular decision boundary, x is equals to 0. So I can see that there is no misclassification. So this is my optimal solution, that is x is equals to 0. Followed by that, if I take y is equals to 0, what will happen? So if I take y equals to 0, now you can see this is the line y equals to 0. So now you can see that you are incurring so many misclassifications. You are saying that the upper half is class 1, lower half is class 2. So what about these points? These points are misclassified. So y cannot be the solution. Then x equals to y. X equals to y means this particular line. This is 2 comma 1, so it will go like this. So this is the line. Now you can see the margin over here, it is less. What was there in case of x equal to 0? You have a wider margin. Now you can see the margin is less, margin value is less. So that means again this x equal to y will be nullified. And similarly you can find the logic. You have got the logic that margin should be maximized, and the maximum margin you are getting in case of x equal to 0. So that is why your classification or the decision optimal decision boundary will be given by x equals to 0.
Then, sir, those points matters or no, x and y which are given? Like by looking at the options only we can make out, sir.
Yeah, as because you are dealing with simple problems. For example, here you have only 2 points. That means your feature vector x is R2 cross 1. But consider you are working with MNIST problem. The data set that I showed in the last class, MNIST problem. MNIST has data shape of 28 cross 28. So as per the lecture provided by Professor Biswas, so you can convert this 28 by 28 image to an 1D array, So then your shape will be 28 cross 28 cross 1 or 784 cross 1. So now you can see, instead of having 2 dimension, now you will be having 784 dimensions. So to visualize those problems, it is very difficult. For these kind of questions, you can just directly see the points and you can answer the question. But in terms of real life problems, it is very difficult because your feature dimension will be very high in terms of 1000, in terms of 10,000, something like that. So for solving these mathematical problems, again I'm saying the same line, for solving mathematical problems to get it done with the quizzes, the questions are very easy. You can just plot them and you can get the result. So rather than doing analytical solution, you can just do the visualization. So visualization will give you a good hand on solving these kinds of problems.
That means, sir, for two-dimensional, always it is x is equal to 0, only the boundary.
No. For example, if I change the particular point positions, let's say this is your what you call, this is the xy coordinate, and your points are distributed like this, class 1 and class 2. Then you can think that this will be the decision solution, because this gives you a wider margin. This gives you the wider margin. So depending on how your points are oriented, you have to decide. Let's say your points are distributed like this. This one. This is class 2 and this is class 1. Then you have to see, okay, if I choose this one and then you look at the support vectors, this will give you the optimal solution. So it is not necessarily that not necessary that x equals to 0 have to be the optimal solution. It will vary when these values will change. So given the orientation of the feature, your support vector, your classifiers, your classification boundary will also change.
Sir, then for the condition y is equal to 0, how the data point should be, sir, then?
Y equals to 0. Okay, y equals to 0, yeah. So in the previous question you were talking about, right? So
Yeah.
in this particular scenario, right? So in this particular scenario, you can see that that this is y equals to 0, right? So
Yes,
if
sir.
you choose that this is your optimal solution, now you can see that the data points itself are lying on top of the solution boundary. And over here you can see that you have cut the plane in two halves, that is half 1 and half 2, and while doing so you are only classifying these two points. However, what about these points, that this green point, this red point, at the in the last class, probably I think I showed you one problem like this. In case of Bayesian minimum risk class, minimum error classifier, you have two classes, p omega 1 given x, p omega 2 given x. If your feature is lying at this position, so the feature will be predicted in what class, in which class? If your feature is at this particular position, sorry,
Plus 2. W1.
W1. So this is omega 1. So probability for omega 1 is higher. And if feature lies on this region, so probability of omega 2. So this is omega 2. Now what about at this particular position where these two lines intersects? So at this particular position, P omega 1 given x is equals to P omega 2 given x. That means over here you cannot decide, can't be decided. So at this location y equals to 0, you can see that green line, green point is also on the decision surface, red point is also on the decision surface. That means out of these 1, 2, 3, 4, 5, out of these 5 points, 3 points you are not able to classify. That means choosing that particular solution is of no use. So therefore, we omit that particular solution. Your decision boundary should be such that it gives wide margin as well as it gives wider confidence while classifying. Now for these points, these red points and this green point, your confidence of classification is 0, as because you are not able to tell that which class they are coming from. So therefore y equals to 0 is not the optimal solution.
Sir, when we are calculating the margin on the bottom right corner, how do we know what is W? What is the W vector?
That
Because
W,
we know x plus x minus.
so that W is what has to be trained. You need to train a model. So while training, you actually learn these W's. What you do, for example, you initialize with any random value. If you start an epoch, you initialize with any random value. At that particular position, let me just give you a glimpse. So you have two class problems like this. When you choose any random value, your problem at hand is to, this is margin should be maximized, and with constraint that yi xi into w plus b should be greater than 1. So this is the condition that you have to satisfy. Now if you choose any random w at, let's say, iteration 1, so it chooses a decision boundary like this. So that means you can see you are doing huge amount of misclassification. You are doing huge amount of misclassification. You cannot predict that these two are coming on the same half. So that means they might be of same class, but it is not the case. So you incur loss. So this loss should be minimized. How the loss should be minimized? Using gradient descent. Now you
Sir,
do gradient descent. Yeah.
Sir, one more thing, along with this condition yi into bracket xi w plus b greater than 1, should we also have another condition where w is perpendicular to the x feature?
Yeah, obviously it is already there. Your initial condition was wx plus b equals to 0. Now think it in terms of a matrix. In terms of matrix, if you think, so let's say x is of r d cross 1. So what you can do is x1, x2, dot something, xn, and you have a b over here. So your weight matrix looks like this. So this is d cross 1. So your weight matrix is of 1 cross d, w1 to, let's say this is d, wd. So if you multiply these things, so you will get w1 x1, w2 x2, wd xd plus b is equals to 0, isn't it? Now you absorb this b term inside this weight matrix. Now I will be writing as w1 to wd in as well as b inside this weight matrix. And to do that, compensate this thing. So I can write this only b thing as b multiplied with 1. So x2 1 is equals to 0. So now my modified equation will be w hat x hat is equals to 0. Now think it in terms of any matrix, any vector problem. So this vector problem is what? If you have a W matrix or if you have a x vector over here, the dot product is 0, that means obviously they are orthogonal to each other. So these are basic constraints. W has to be orthogonal to the vector, the feature vector.
Okay, thank you.
Sir, in the scenario y is equal to 0, if you are
Yeah.
saying y is equal to 0, then the data point should be few will be on the upper side and the few will be on the below side. Then only y is equal to 0 condition lies, right, sir?
Yeah, at y equals to 0, you can see there are 3 points. You have total 5 points. 1 second.
Not with respect to this, sir. This I understood. If you
Yeah.
if you want to have y is equal to 0, how the data point should be, sir?
Okay. So ideally it should be you just need to check that the margin should be maximized. If you have a support vector from this particular class, it should lie over here. If you have a support vector over here in this particular class, so this margin should be maximized. So this could be a one scenario. Another scenario could be, let's say you have a data point over here, you have another data point over here, and rest of the data points are like distributed like this. They are concentrated at this particular position. Over here they are distributed at this particular location. So you need to, these your support vectors, and y equals to 0 is the classification boundary. So you always have to think that you need to find the support vectors, that what are the points which are having minimum orthogonal distance, because these points have higher orthogonal distance than this. So you need to find always the support vectors, and then given the support vectors you can decide any sort of uh, what you call decision boundary based on the SVM application.
Sir, my previous question, in a two class problem which we solved, how do we calculate W?
Yeah. So um, yeah, so till this point, I think you have understood, right? So initially,
Yes.
you have to train a model. So you have to train a model means you will be determining these W's such that your margin should be maximized, as well as this rule should also be followed. So you need to find these W's over the iteration. So how can you start finding the W? You can initially take any value, any sort of value. So you can randomly initialize the values of W. So let's say in iteration 1, as you have randomly initialized in all the values, your decision surface is like this. That means you are doing very bad classification. So you incur some loss. It could be hinge loss, it could be any other loss. Now as soon as you incur a hinge loss value, that means this loss should be minimized. If you minimize the loss, that means your classification will be good. So how to minimize the loss? Using gradient descent. Now with respect to what you are trying to minimize the loss, with respect to this W you are trying to minimize the loss. So over here your gradient descent update rule will be what? Wk plus 1 will be equal to Wk. That means in previous iteration whatever W were there, and then you will update it like this, minus eta into gradient of loss function with respect to W. Or if I write it more clearly, it would be eta into del L by del W. So you start with iteration 1, let's say after iteration 20, the scenario is something like this. So you have the orange class over here, you have the red class over here, and you are getting a decision surface like this. So still you are classifying it well, but still your margin is not maximized. So you go up to, let's say, 200 epochs. After 200 epoch, you get something like this. So at this particular condition, the margin is maximized. Let's say you are getting loss value is equals to 0. So if your loss value is equals to 0, that means this del W, this all thing will go vanish. That means at the final iteration, let's say iteration 2000, the final weight value will be W2000 is equals to W1999. So in this way, every iteration your W values are changing, and whenever you incur loss equal to 0, that means your iteration will stop there. So in this way, the training process occurs and you learn the W.
Okay.
Okay. So what are the 1 second. Okay. So for 2-class problem, minimum possible. Yeah. So the question states that for a 2-class problem, what is the minimum possible number of support vectors? Let's say, assume there are more than 4 examples for each class. Let's say you have uh, 5 data points. Similarly, for this class, let's say you have 6 data points or 7 data points over here. So you need to find minimum number of support vectors. You need to find minimum number of support vectors. So let's say this is another one. So you need to find the optimal solution. So let us consider that the optimal solution is this one. Again, the image doesn't look to be an optimal solution, but let us consider this is the optimal one. So the support vectors are this one and this one, because if you start extracting the orthogonal distance from this point to this point, from this point to this point, even from over here to here, so you can see that they have higher distance, orthogonal distance. But for these 2 points, you can see that for these 2 points, the orthogonal distance is minimum. So these are called support vectors. And as because you have 2-class problems, so you have to have at least 2 support vectors from each of the class to ensure that you are doing proper classification. Because if you just think that these to be, if you just think like a condition over here, so your optimal solution, let us think about it. The optimal solution is this one. So now you can see that for the red class, okay, for the red class you have very high margin, very high confidence, because the distance from the red class to this green line or the decision boundary is very large. But for this particular class, you can see the margin is very less. That means you are not doing a good classification. So you need to again shift your decision boundary to at this particular location, such that you ensure margin for both the classes should be maximized. Therefore, you at minimum you will be having two such support vectors in a two class problem. So over here it will be 2, because at least two support vectors needed from each of the classes. One support vector should be needed to ensure that you are doing good classification. That means you have to have good margin for both the classes. It is not like that in this particular case where you have very good margin for this red class and you have very poor margin for this particular blue class. So over there you need to think about that margin should be maximized in terms of both the classes. So therefore you need to have at least two number of what you call the support vectors.
Sir, what is the
Sir,
meaning of that? Assume there are more than 4 examples for each class.
Assume there are more example for each class means these data points are greater than 4 for each of the classes. These data points are greater than 4. That means you have x1, x2, x3, x4, x5 likewise. It should be the number of observations should be greater than 4. Xi you have xi number of observations, I should be greater than 4.
Okay, sir. So, sir, in general, we can say that for two class problem, it is two support vectors. Means for n is equal to n, sir, in general.
Again, the thing is that you need to, because at this particular condition, you can see that to get a, let us consider you have 3 class problem like this. It's like this. So at this condition, you may not encounter the same problem, because let's say for this particular line, the support vector is this one for this particular class. Now for this particular line, the support vector is this one. Now for these two cases, again you have this as support vector, and from this side you have another support vector. So it is not necessary that you will be having for n class n number of vectors. So depending on how your decision boundary is looking like, the support vector numbers will also change, because you can see to decide this particular line to be an optimal line, you need two support vectors. To decide this particular line to be a optimal line, you need two support vectors, one from this side, one from this side. Right. So in this way, you can visualize the problem. That means for n number of classes, you cannot just generalize it to as n. It is based on the distribution. But in case of two class problem, obviously there will be one solution line which will create a half space. And as this is a half space, so there should be 2 points which will tell me that, okay, margin from this particular from this line to omega 1 should be this one, margin from omega 2 to this one is something else. So the margin should be maximized. So that is why for two class problem it is 2.
Sir, so even for two class problem, we can have n number of support vector, right? Maybe all of them are not optimal.
Yeah. You can get even more than 2. That is why the question is minimum possible. You can, it may so happen that you have another support vector lying over here. It may so happen that you have another vector lying over here. So you can get n number of you can have n number of such observation which lie on the edge of the support vector region. But the minimum number should be 2 for two class problem.
Sir, if we fix a decision boundary and then margin is drawn, is it possible that the data points come inside that? Now, whatever examples you have shown, all the data points are outside and there is only one point which we fix it as support vector.
It may so happen. Yeah. Your query is correct one, because in all of the cases, I have shown the images such that your classification accuracy is 100%, because there is no such data point which is coming at this particular region, or it is going in the other way around. So in each and every cases, I am showing the 100% result, 100% classification accuracy based images. But it may happen because you cannot ensure by training, because that gradient descent based iterative approach is also kind of, it starts with a random value, rand of something, and then it tries to minimize. So in case of deep learning, or in case of any optimization problem, you may have several local minimas. Let's say you are stuck at this particular local minima, or let's say you are stuck at this particular local minima, and you are not able to go out to this global minima. Then it may so happen some of the data points will be misclassified. Our aim is to classify with a great support, great margin, but it may so happen that some of the points will be misclassified. So this is a common thing that you can observe in machine learning, deep learning. So even if you train, it is not mandatory that you will get the 100% accuracy based decision surface. There should be some errors or misclassification, what you call. Okay, so these are some of the numerical problems. So you have a vector v with 2i 3j minus 2k over here, and you have a plane over here. So you need to calculate the perpendicular distance. So how you do the perpendicular distance, that is 2 plus, you just put these values over each of the coordinates. So 3 will be placed over here like that. So 2 into 3, and then 2 into minus 2 plus 5 divided by norm of this particular vector. So that is norm v. That means you can extract norm v as root over 2 square, 3 square, 2 square, and then you can solve it, and you will get the final answer. So this is how you can proceed with this kind of questions. So this is the distance metric. Okay. Another question that I have is, so what is hinge loss? What is the expression for hinge loss? It is maximum of delta minus some score. I'm not exactly writing the equation that is there in case of multi-class classification, but this is the in general hinge loss equation. So it is there in probably lecture 4 of week 3. So there is a huge elaborative lecture is there. You can refer to that. So in case of two class problem, that means binary SVM problem, our main classification rule was what? Yi multiplied Wixi plus b should be greater than equal to 1. That means the margin value or the delta is 1 over here while training. So 0. So this delta is 1, and this is this code. Now, how come this code is coming? Code is coming from this multiplication. So whenever this multiplication will be greater than 1, that means you are doing good classification. There is no error. If you are doing misclassification, that means it is below 1. So this code is coming from this particular multiplication. So over here, what is basically the statement? The statement is y is the class level, got it, and p is the predicted value of a class. Now the predicted value of a class actually comes from this particular equation. That means if you have any feature vector, I think you have seen that you have a weight matrix, a image was there, there is a barred image, then you are extracting feature, then you are multiplying these features with these weights and adding with the bias. So this gives you some score value. So along with that, over here in case of binary SVM problem, you multiply with it with the class level as well. So the multiplication is yi, and this is they have mentioned as p. So yi into pi. So in general, I can write it as y into p. So 1 minus y into p. So this code is uh, turns to be y into p. So the final what you call the hinged loss expression will be 0, 1 comma minus yp. So option A is the correct answer. So you can go back to the hinge loss part and you can check how hinge loss works, because as you go along with this deep learning lecture series, you will see there are several loss functions you will encounter several loss functions and several optimization techniques also. In the next week, the optimization technique will start. So it comes with huge mathematics. So I will rather request you to reproduce the mathematical expressions by yourself. Whatever you are seeing in the lecture, after seeing the lecture, you try to reproduce it by yourself. And if you find any difficulty, then you can again check the video. So this way you will get a hand on this particular course, because this course is rather very much theoretical. So you need to have a better hand on the derivation parts as well, because in the final examination you will see questions that are coming from the derivations as well. Because this hinge loss, as far as the hinge loss is concerned, I have skipped about the description of hinge loss, because that is beyond the scope of beyond the scope of me as well, because this is a 2-hour lecture. I cannot start discussing the whole theory that is covered in the week itself. So I request you all to reproduce the mathematical derivations that is there in the uh, course website, or the lecture materials that you are getting in the NPTEL website itself. The lecture materials are also provided for the week slides, so you can refer to those. Okay, so if you have any further questions, then we can discuss. Otherwise, we can end the session.
Sir, one question on the previous slide. That square root mod of vector. Yeah. Should that be the mod, the vector mod, or would that be square root of the coefficient from the plane?
Okay, let me. I may have done mistake. Let me just check. So it is 2 plus 6 minus 4 plus 5 over here. So this is 2 plus 2, that means 9 over here. And then it's 1 plus 4 plus 4. So and it is 4. Then you have 9 and you have 4. 13, 17. Let me just see, because I also I think probably have mistake. Normalized distance from point to plane. Okay, it will be the coefficients. Yes, it will be the coefficients. So it will be not the norm of this particular solution vector. It will be rather the norm of, let me call it as W, let's say. So it will be norm of W. So from norm of W, you can get the final answer. So denominator you will get 3, and in the numerator you got 9. So it will be 3. Yeah, thank you for correcting me.
And sir, can you also explain how geometrically this can be visualized? Like we have a plane, we have a point, and then we must be doing the distance, right? And
Yeah,
projection.
yeah. So let me visualize it in 2 dimension. So let's say you have a line over here and you have a point over here. So let's say it is ax plus b equals to c, ax plus by equal to c, or and you have a point b comma e. So yeah, so first what you are doing over here is you can consider this also as a vector. Now how you can consider it as a vector? Just you do it like this: ax plus by minus c is equals to 0. So again, in terms of if you think it in terms of the matrix multiplication, so your x and y are the feature vector x comma y over here, and a and b and c, these are the weight matrices. So let us consider this is the weight matrix. So this weight matrix, what it will do is basically, if I write the equation in like this: c into 1 is equals to 0. So you have a, b and minus c multiplied with x, y, 1 is equals to 0, right? So this is w, this is x is equals to 0. Now you are doing the orthogonal, you are measuring the perpendicular distance or orthogonal distance or normalized distance, normal distance. So these all terminologies you will encounter: normal distance, orthogonal distance, or perpendicular distance. Perpendicular distance. So you are taking a dot product between this particular vector and the plane or a vectorized representation ABC over here. You are taking dot product between these two. But this is not the only thing that you are doing. You are doing w dot x. This is not the only thing that you are doing. You are taking a normalized distance. So whenever you encounter the fact that normalization basically normalization, let's say you have a complex complex variable a plus jb. You can normalize it by two techniques. One is, you will find in it again in the probably week 12 or something, you will see min max normalization, you will see z score normalization, you will see that magnitude or L2 norm. So this L2 norm basically refers to this normalized distance. So that is why you take a normalization factor. So this is not just a modulus operation. This is called an L2 norm based normalization. So as because we are actually focusing on the dot product, as well as this is not a simple dot product, this also associates with the normal distance. So that is why L2 norm comes into the picture, and that is why you divide this whole thing by this L2 norm of W. And that is why, as because it's an L2 norm, That is why you always draw two lines. So that is the main aim. So you have L1 norm. L1 norm is what? Absolute value. L2 norm is what? Root over a square plus b square to the power half. So likewise, you for the normal distance or for the orthogonal distance, you choose a normalization factor, which is itself is an L2 norm of the vector, is L2 norm of the plane on top of which you are taking the projection. So that is why this is the visual interpretation. You have a plane over here, you have a point over here, you are taking the dot product between these two, and as well as whatever unit vector it has, this unit vector has also to be considered. So if you think in terms of unit vector, W divided by W is the unit vector. So if this is the, let's say, plane, it has a unit vector, normal unit vector, and you have a point over here. So this is like this. So you are taking dot product between these two. So this is like this, and you are taking dot product like this. So this will give you the normal perpendicular distance from the point and the on top of the unit vector.
Understood, sir. Thank you very much.
Sir, one question. How you have calculated denominator, sir, that square root of 1 square plus 3 square plus 2 square?
Yeah, 1 square plus 2 square plus 2 square.
But there is no 1, no, sir. There is only 2, 3, 2 minus 2 it is.
No. It is the let's say this is the weight, this is the W function, and it has the coefficient. So it is the norm of this particular coefficient. So 1 square plus 2 square plus 2 square is coming from this thing, not from this one. Denominator is not norm of this particular vector. So over here that I have written, over here also, if I write that W is ax plus by minus c, so I will consider the unit vector. So unit vector means I need to take norm of W. That means mod a square plus b square plus c square root over. So that is why 1 square plus 2 square plus 2 square.
Okay, sir, got it. Thank you.
Sir, can you just go to the previous slide? No, sir, that class labels, how do we give that class labels, sir? -1, +1.
Okay, let me see the problem. Yes, this one.
No, so we had a table form where points are given for x, y, and the class label is given. Yes, sir. What is this +1, -1 mean, sir?
+1 means, let's say, class omega 1, and -1 is class omega 2.
Oh, okay.
So they just have written in terms of some other nomenclature. Omega 1 they have written as +1, -1 they have written as minus. Omega 2 has written as -1. Okay, so any further queries?
Sir, one question. Can we carry the calculator in the final exam?
I think you can carry the final calculator. I think I'm not sure. It will they will provide you the guidelines. But what I will suggest is that you while doing these problems, you can use the GATE online calculator. Uh, GATE exam. So that GATE exam online calculator. Because
And
at
that would
my
be accessible?
yes, go ahead, please.
Yeah, that GATE online calculator would be accessible from the exam.
Yeah. It is just an so let's say this is your while writing the exam, this is the page. So on the right hand side, there will be a calculator sign. So if you tap the calculator, a calculator board will come over there. You can see the operations, and uh, uh, you'll be using that particular calculator only if they don't allow. But let me tell you, this gate calculator is bit tricky if you are using it for the first time. So for all of you, I recommend you to start using this gate calculator because it will help you. Otherwise, if you go on the go to the exam and for the first time you are using the calculator, you might get a problem. Why? Let me tell you. Generally, in the scientific calculator that we use, for example, if I have to write sine of 90°, so first thing that we tap in the calculator is sine button. Then a box comes, then we go to that box and we write 90 and then press equal to. But in case of gate calculator, things are just the reverse thing, just the opposite. You first need to choose 90, then you need to choose sine. So you'll be writing the exam for let's say 2 hours or 3 hours, and you've been given some big calculations, and you are using the calculator for the first time. So then you will get into trouble because you'll be encountering those problems for the first time. So beforehand, I will recommend you to get the software, get online calculator. It is there in public mode. You can download any software, get online calculator, and you can start using that particular calculator only.
Thank you, sir.
Okay. Okay, so in the next session in week 4, we'll solve the week 3 quiz, as well as I will do the hands-on session for the week 3 SVM classification, KNN classification and all. So let me just stop sharing.
Thank you, sir.
Yeah.
Thank you, sir.
Yeah, thank you.